So the first thing you're going to want to do from your local machine is log into Theta, and from the login node, then log into the GPU service node, the Theta GPU service node. Once you're in there, hopefully, you're going to want to Q sub 1 hour. An interactive session. Hopefully all of those are correct. Yep. Hopefully I can get on. If not, I have a session running, so it shouldn't be a huge issue.
You might be limited to one.
Oh, there it goes.
No.
Okay. So yeah, the other one was on a different queue. So all right, no problems. So the launching this interactive session works. Once you're in this interactive session, you're going to want to navigate to wherever you cloned the GitHub repo. Make sure you're up to date. So do a git pull. From in here, you now want, the next thing you are going to want to do is load the most recent Conda module, which has all of the machine learning frameworks already installed. So this is all contained in this launch Jupyter notebook.
Sam, could you increase your font size a bit? Thank you.
There we go. Now it's on my line. Better. That's better. You can see it.
Yes, thank you.
Yeah, no problem. And so all of this information about loading the modules and stuff is contained in this this launch Jupyter notebook Theta GPU script. But just for the sake of people seeing how this is done, you can make sure you've loaded the correct module. Oh, I haven't loaded it yet. So you're going to want a module load Conda, this most recent one, which is 922. Once you've loaded that module, be sure and Conda activate base to activate the base environment. Which, okay, should hopefully take a second. Once you've got the base environment activated, you can go ahead and launch the Jupyter notebook. So there's one kind of small technicality about this, is that the Jupyter notebook, the Jupyter kernel will actually take up one of these GPUs. So when you launch the Jupyter notebook command, you're going to want to reserve one for that. So CUDA visible devices 0, 1, 2, 3, 4, 5, 6. You can specify a port. Not terribly relevant, but that's the basic idea of the command. Oh, that's going to give me a problem. So should specify the port. There are multiple ways of doing this. I think it might be a little bit different in the shell script, but the idea is all the same. Once that should be started, sorry. Forward the ports to Theta GPU. Make sure you know which actual GPU node you're on. So in this case, it's Theta GPU 10. I prompt you for your password. All right. And then I should be able to. Uh-oh. I'm not sure why this isn't working. Okay, so I have a backup for in case that happens. Let's try this again. This should work. So okay, there we go. Yeah, I'm not sure why it wasn't working before. So now you've connected your local machine to the data GPU node that's you're running in the interactive session. From here, you can then just go ahead and open up the notebook. Hopefully this should be pretty straightforward. Make it a little bigger so everybody can see. All right, and so now we're in the Jupyter notebook running on data GPU. And so now we'll go through this. So just to give some kind of overviews, there's a table of contents listed here showing each of the different sections, what we'll be going through. And so like Romain said, this is based on materials from this Keras tutorial on hyperparameter optimization. So a lot of the data set and things like that are all going to be taken from there with the necessary modifications to get it run in using dpiper. First, so you need to make sure this nested async IO is installed. Yeah, basically just because this Jupyter uses Tornado, which already starts an event loop, and so you need this kind of little hack to make sure that it runs correctly. That should install without problems. Hopefully nobody has any problems with that. If it says that it defaults to the user installation, that's fine. That's where it should go since you won't have write permissions to install globally. Next, these are just kind of settings so that the outputs doesn't get all cluttered with a bunch of debug statements that are distracting. The next step is, or next kind of point to note is this import strategy. So you need to be sure and actually call and import TensorFlow using this import TensorFlow as TF. In the original Keras tutorial that a lot of this material is taken from, they use this kind of from TensorFlow import Keras strategy, which can lead to serialization errors in the data and basically crash the search. So you need to be sure. And when you're actually doing your imports, you need to make sure that you call it as this import TensorFlow as TF. And it might take a second to start up.
Do we know why that is? I mean, it seems like importing the Keras subnames should also import like the tensor E. It doesn't obviously import all of the TensorFlow namespace into your namespace, but it should at least do the initialization. Just curious.
That's a good question. I'm really not, so I'm not entirely sure. So I know that there are kind of these subtle differences between using the base TensorFlow and kind of using the higher level Keras wrappers around things. So yeah, I'm really the root cause. I'm actually not sure why, which is actually a good question. But yeah, maybe Romain, do you have any idea as to why that is?
So sometimes in any frameworks, in imports, you don't have just definition, you actually have declarations, affectation of some variables, right? And so when you use Ray, you basically, Ray is basically gonna serialize all the local variables and try to send them to initialize remote workers to do remote calls. And sometimes some of these data are not serializable with Pickle or Cloud Pickle, and that's why you can't do this. If you just use the TensorFlow, import TensorFlow as TF, you will have lazy imports that will be imported dynamically when you access the stuff, and it's very different. It means like the import will be performed within the worker directly, and you will not serialize the context.
Yeah, okay, that makes sense. That yeah, if otherwise you have these lazy imports that end up being dynamic and done as they're needed. That kind of makes sense actually. But yeah, so really the takeaway is that you need to be careful about that. So then once your imports have all completed and everything, you then can run these kind of simple functions that'll basically determine the total number of available GPUs or that you're running on, and set that to, in this case, we should see 7 or 6. Oh, yeah, right, because I only initialized it with 7, and one of them is taken up by the Jupyter kernel. So in any case, we have 6 GPUs available. Then once that's all initiated, just a brief overview of this data set that we're going to be working with. So this data set is provided by the Cleveland Clinic Foundation for Heart Disease. And so like I had said, this is all just mostly borrowed from this Keras tutorial, and just for completeness, a description of each of the features is included here. So you have things like the age. One thing maybe worth pointing out is that some of these features are numerical and some of them are categorical. And that just changes a little bit how the actual features get encoded in the model. So it's a little bit important to take note of. And obviously in a real world case or your specific application, it's important to kind of know how these features are encoded in the model. Then next we have some kind of helper scripts here that are helper functions here that basically just load in this data, which is downloaded already and included in the GitHub repo, but it came from this URL originally. Then it reads in the data and basically converts it to a pandas data frame. I think that ran already, yep. Next, we have these functions that encode different types of features differently. So we have this first one on the top that encodes numerical feature. Basically, yeah, just doing this layer normalization to learn the statistics of the data and then return this normalized encoded and this normalized encoded feature. Similarly, there's a function here that encodes a categorical feature. So more or less the same idea. The details of this aren't terribly important, but are basically just what is used for this specific model. And so that's what's needed. Next is the definition of this run function. So this is kind of important because this is the actual function that defines the objective that we want to that DeepHyper will then try to maximize. It takes as input a config dictionary that returns us, and returns a scalar value that the hyperparameter search will then try to optimize. So the config dictionary contains a sample value of the hyperparameters we want to tune. And so in this example, some of the hyperparameters we'll be looking at are things like the number of units in the hidden layers, the different activation functions, different dropout rates, the regularization, number of epochs, batch size, and the learning rate. So these are kind of standard hyperparameters that you might want to optimize in your machine learning model. And so, like I said, this run function takes in a config dictionary and then basically goes through setting up the model. So loads in the data, converts it to this data set, splits it into training and validation data sets separately. Then it goes through and creates in the inputs for each of the features that we're interested in. So in this case, these are all of the features included in this data set table. And yeah, basically creates an input layer or an input variable for each of those. Then basically concatenates all of them into this list of all inputs. Each of these features then get encoded using that function above to encode either categorical or numerical features and returns this, yeah, basically encoded feature for each of these inputs. And then and then we stack all of them, concatenate all of them into this using this list of the encoded features. Those features are then passed through a simple dense layer, which has not the number of units in this layer is determined by the key value pair specified in our config dictionary. And similarly with the activation function, following that dense layer, we then have a dropout, which is again determined by a hyperparameter that we want to optimize. Finally, the output is then the final layer. Following that is the output, which uses the sigmoid activation function. And then our model is basically just that. So this description that I just went through, all of the encoded features then pass through a dense layer followed by dropout, and then a sigmoid activation function following the final output dense layer. So that is our complete model. We then define our optimizer that we want to use. Again, using a learning rate, which is a hyperparameter that we are going to optimize. Can then compile the model and fit it, basically giving this, the output is this history, and the metric or the objective that we are trying to optimize is then the validation accuracy of this history. So this is a scalar value returned by this run function. And one thing that's important to note, yes, so this objective is the objective to be maximized by dpiper is the scalar value returned by this run function, which I just went through. And this, this specifically in this tutorial, it corresponds to the validation accuracy of the last epoch of training. Again, which is just shown in this little snippet here. We can then evaluate our model using just a default configuration dictionary. So just to pass in some default values and see what we get. Did I not run this? Always run a little risk trying to do things live, right? I think it's working this time. I think I forgot to run that function or run that sub. No. That is all right. So let's try it all again. Start from the beginning. So I'll just run through these since I've explained them all already. Hopefully things work this time. I'm not sure what exactly that problem is. Let's see. Okay, yeah, it seems to have worked this time. No, it didn't. Okay, let's try this backup notebook that I had. So continuing from that point, just for the sake of continuity. Okay, I'm not exactly sure what was happening in that other one, but so you can see here now, running the model using this default configuration dictionary specified here gives us validation accuracy of 82%. But we would like to try to improve on that so we can define this hyperparameter optimization problem. And the idea behind setting up this hyperparameter optimization problem, which is defined in this deephyper.problem HP problem. So we can first initialize it and then add hyperparameters for each of the hyperparameters we wish to optimize. So in this case, we have the number of units in the dense layer, which will be sampled from a uniform prior over the range of 8 to 128. The different activation functions we want to consider. So yeah, things like exponential, linear, yeah, basically just a whole bunch of different activation functions that we wish to consider. For things like this that are categorical, they'll again be sampled uniformly from this set of activation functions. For real valued hyperparameters, such as like the dropout rate, obviously, which is continuous, it'll again be sampled uniformly over this continuous interval. The number of epochs again is discrete. So this will be sampled uniformly from this range, 10 to 100. We can also specify, so for things like the batch size, we can use a log uniform, or it'll sample, we can explicitly specify that we want this interval to be sampled using log uniform, which will space things out a bit more. And similarly with the learning rate. So that basically allows you to cover a larger range of possible values, basically by using this log uniform. Right, and so then once we've added all of these hyperparameters to the problem, we can then add a starting point, which we'll just use the default configuration as our starting point. And so it'll spit out here the configuration space object. So it'll list out all of the different hyperparameters and each of their choices basically, or the range that they are defined over, as well as this starting point. So this is the default configuration dictionary that we had above, and just the point that we're using to start the search from. Once that has all been set up, we can then define this evaluator object. And so this allows this evaluator is basically what actually runs the search. So it is a standalone object which executes the execution of the Ray remote tasks. And so all they need to be instantiated is just a run function, which is the method defined above that we looked at. Yeah, basically, and then once all of that is set up, you can then just run, the evaluator will then run on all of the available resources, depending on the specifics of how things are being ran. But we've included this kind of helper function that takes as input the function that you want to, that deephyper is trying to optimize, and takes other things as input, so like the number of CPUs, GPUs, how many GPUs to assign to each task. And then it basically creates this evaluator and prints out some information about it and then returns it out. So like I said, the function that we defined earlier, this run function, is the function that to be optimized, that gives us the scalar metric that measures the performance of the model. And so we can run this to get our evaluator, and like you see, it creates this new evaluator, and it should hopefully, yes, have noticed all available GPUs. In this case, we have 6, and we'll assign to each of those GPUs an individual evaluator. Next, there's a bit more information maybe about the asynchronous model-based search. So I won't go over this in too much detail, since obviously a lot of this information was covered in the previous talk, but yeah, this is the basic algorithm here, basic idea of how it works. Yeah, so I won't go into this too much. All of the detail about everything is here if anybody has any questions.